In this video, we present our work, MonoAvatar++, efficient 3D implicit head avatar with mesh-anchored hash table blend shapes. MonoAvatar++ is a controllable head avatar built from monocular RGB videos. Our avatar can be animated and rendered in real time, and still synthesize high-quality 3D head animations. Building controllable head avatars has attracted lots of research attentions due to its rich downstream applications, such as AR and VR communication, virtual try-on, and visual effects for movies and video games. For many applications, real-time running speed and high-quality visual outputs are the fundamental requirements of the avatar to ensure good user experiences. However, existing monocular head avatars cannot fully satisfy these requirements. Some works focus on designing high-quality avatars with vivid expressions, but suffer from slow rendering speed, such as taking several seconds to render one image. Some other works improve their efficiency, leading to faster rendering. But their avatars suffer from inferior rendering quality, leading to stiff motions and artifacts on challenging expressions. To address the issue, we aim to design a novel high-quality, controllable head avatar supporting real-time rendering. Inspired by prior works, we adopt instant NGPs with volumetric rendering to enable fast and photorealistic image synthesis. To extend this design to support controllable expressions, we introduce local hash table blend shapes, which is a mesh-anchored and expression-dependent version of instant NGPs. Our avatar starts from a parametric head model, which gives a mesh under the input expression and pose with a predefined topology. We then attach multiple hash tables on each vertex with learnable embeddings as the table values. These hash tables act as per-vertex local blend shapes. These mesh-anchored blend shapes are then linearly merged with expression-dependent weights, which are predicted by a UNet in UV space from vertex displacements. The UNet also outputs per-vertex features. As a result, we get a head mesh, where each vertex has a merged hash table and a feature vector. Finally, we decode this mesh into a neural radiance field and render the output image with volumetric rendering. Now, we introduce the details of decoding the mesh into the radiance field. The decoding starts with our hierarchical k-nearest neighbor search. We first split the 3D space into a coarse voxel grid, then find K nearest neighbor vertices for each voxel center, and cache them in the voxel as candidate vertices. For a query point, we can find its k-nearest neighbor vertices just from the candidates cached in the voxel that the query point falls in. Thus, we do not need to search over all vertices and hence improve the efficiency. After getting the k-nearest neighbor vertices, we pull the embeddings from the attached hash tables via hash encoding. The pull embeddings are interpolated based on the query point coordinate, and finally fed into a two-hidden layer MLP together with the coordinate and the attached feature of the nearest vertex, to efficiently predict the density and the color, which form the radiance field. Our MonoAvatar++ is a person-specific model. Given the monocular RGB video, we first run face tracking to obtain expression and pose codes, as well as camera parameters of all frames. Then, we can input the tracking results into our model to get the rendered images. Finally, we compute photometric losses between ground truth frames and rendered results to train our model. Our MonoAvatar++ works on various subjects and can produce vivid animations on expressions with personalized details such as wrinkles. We can also handle glasses and produce reasonable geometry shown by the depth rendering. Compared to prior works, our method shows competitive results in both rendering quality and speed. Point Avatar gives overall blurrier results on our challenging data. Insta achieves real-time rendering, but gives foggy results. Nerf Blendshapes produces severe artifacts for several frames in dynamically changing regions such as mouth and eyebrows, and also gives more floaters, resulting in implausible animations. MonoAvatar gives good rendering quality and animations, but is one order of magnitude slower. In contrast, our approach achieves real-time rendering while producing decent visual quality. We also quantitatively verify that our method achieves comparable visual quality to SOTAs with real-time capability, leading to the best speed-quality trade-off. We also build a real-time demo based on our method, where we track the facial performance of the actor with a webcam and render our avatar on a workstation with a RTX 3080 Ti. Finally, we display the rendered stereo pair on a headset and a web page. Thank you for watching.